Okay, so I'm going to show you with the first example. Okay, so in this first example is the basic dehydrations of alcohol, which does not include any carbocation rearrangement. Okay, so there are two types of carbocation rearrangement, which is 1,2-hydride shift and the second one is 1,2-methanide shift. Okay, so the reason why we are making a carbocation rearrangement is to make a more stable carbocation. Okay, so I'm going to explain in more details about this carbocation rearrangement in the next examples. Okay, but in this one I'm going to show you the basic dehydrations of alcohol with no carbocation rearrangement. Okay, so there are three basic steps in your dehydrations of alcohol, which is your first step is the protonation of OH group. Okay, so the dehydrations of alcohol will always involve alcohols react with sulfuric acid, okay, as a reagent, and the condition is heat and reflux. Okay, please refer to your lecture note, okay, on how to write down a correct and balanced chemical equation for these dehydrations of alcohol. Okay, so in this video I will just explain to you how to show the reaction mechanism for the formation of alkenes using these dehydrations of alcohol. Okay, and so I'm having here ethanol, okay, with sulfuric acid. So the oxygen in my ethanol, okay, in the OH group there are two lone pairs. So one of the lone pairs will attack this hydrogen in your sulfuric acid, okay, and we are going to make a protonated alcohol. And since we are making this protonated alcohol, okay, so the bond between the hydrogen and oxygen in your sulfuric acid will break heterolytically. Okay, so we are making a carbocation electrophile and a nucleophile, which is your OSO3H. Okay, so this nucleophile will be useful at the end of the dehydration of alcohol, which is at your last step. So we're going to use it later on. Okay, so with a plus charge here, so this is your protonated alcohol. Okay, so from this protonated alcohol, okay, we're going to move to the next step, which the loss of water in your protonated alcohol. So the bond here, the between the carbon and the oxygen here will break heterolytically. So we're going to form a carbocation CH3, C, okay, H2 with a plus charge. Okay, so this is a primary carbocation. Okay, why do I say it is a primary carbocation? Because the carbon here only bond to one of the carbons. So it's one carbon, that means the primary carbocation. So in the process, we are losing water as well. Okay, so let's move on to the last step, where we involve removal of H+. Okay, so we're going to use the nucleophile that we initially produced in the first step, and then this nucleophile will attack the hydrogen in the carbocation to produce a double bond or your alkene. Okay, so the negatively charged from your nucleophile, okay, please make sure your arrow start from the negative charge of your oxygen and then it's directly attack the hydrogen. So this is the three basic steps in the dehydration of alcohol. If there is a possibility of making a more stable carbocation involving carbocation rearrangement, so we have additional steps before we can proceed with the last step, which is removal of H+. Okay, so in this first example, I only can produce one alkene. Okay, if involving carbocation rearrangement, that is where Set-Zaf rule is applied. The major product of elimination reaction to produce alkene is the one which have highly substituted alkene. Okay, so we're going to see in more details in the few next examples. In my second example, I will show you a reaction which involves 1,2-hydride shift. Okay, so 1,2-hydride shift is an example of carbocation rearrangement. So hydride is referring to hydrogen. Okay, so that means we are moving hydrogen in the carbocation rearrangement. Okay, so I have this alcohol. So I will always start by making protonated alcohol. So as always, this lone pair from this oxygen in the OH will attack this hydrogen, and as a result, okay, the bond between the oxygen and H in the sulfuric acid will break heterolytically, resulting in the formation of protonated alcohol with a nucleophile. Okay, so that nucleophile will be useful at the end of the process, at the end of your dehydrations of alcohol. Okay, here is our protonated alcohol, okay, with a nucleophile. Okay, so from the protonated alcohol, we're going to lose some water to produce a carbocation. Okay, so CH3 here. Okay, so losing water, so let's rewrite your protonated alcohol. Okay, so losing of water means the bond between the carbon here and the oxygen in your OH group going to break heterolytically. Okay, so it's going to break heterolytically, starts from the bond here. Okay, so we are releasing water, okay, and in the same time we are making a carbocation. So carbocation means there is a plus charge on the carbon. Okay, so this is a primary carbocation again. But there are possibilities, okay, for us to produce more stable carbocation by doing 1,2 hydride shift. What is 1,2 hydride shift? That means I'm going to move this hydrogen, okay, to this carbon here, so that this plus charge will be changing to the carbon here. Okay, so let me show you what is 1,2 hydride shift. Okay, so here, okay, so this hydrogen, okay, this bond between this carbon and hydrogen will break and goes to this carbon. So the plus charge transfer. So now instead of we are making a primary carbocation, okay, so actually by making 1,2 hydride shift, we are making a tertiary carbocation, which is more stable. Okay, the most stable carbocation and definitely more stable than your primary carbocation. So this will lead to the major product of your reaction. Again, okay, the nucleophile that we produce in the first step will attack the hydrogen at your carbocation. Okay, so we are releasing sulfuric acid again with an alkene double bond formed between here. So CH2. So this is your alkene. Let's move on to the third example where we have 1,2 methanide shift. Okay, so methanide is referring to CH3. That means during the carbocation rearrangement, okay, we are moving CH3 group instead of hydrogen like in your second example. So if we are moving hydrogen, that is hydride shift. If we are moving CH3 or your methyl, that is methanide shift. Okay, so we always start by making protonation of the OH group. Okay, so again, the lone pair from your oxygen in your OH group will attack the hydrogen in your sulfuric acid, and the bond between the oxygen and hydrogen will break heterolytically, resulting in the formation of your nucleophile and your protonated alcohol. So your protonated alcohol have plus charge on your oxygen. Okay, okay, so next step, okay, from the protonated alcohol we are losing water so that we can form carbocation. Okay, so the bond between this carbon and oxygen in your alcohol will break heterolytically. Okay, so we are losing water and we are making a carbocation. Okay, so in this one we are actually making a primary carbocation because the carbon here in your plus charge is directly bound to only one carbon, so this is 1 degree carbocation. Okay, so there are 2 methyl groups present in your next carbon. That means there are chances to make a more stable carbocation by doing 1,2 methanide shift. The group will break and will go to the carbon in your carbocation. Okay, so now, we are making this with a plus charge here and CH3. Okay, so right now we are making a tertiary carbocation, which is the most stable carbocation in the series and definitely more stable than the initial primary carbocation that we make in the step 2. Okay, now so we are ready for the last steps, which is the removal of H plus to produce your alkene. Okay, so this negatively charged will attack this hydrogen here, and then the bond between this carbon and hydrogen will break and all the electron will go here. So we are making here CH2 double bond C and CH3 plus regenerate your sulfuric acid. Okay, so this is the major alkene products that we produce when there are 1,2 methanide shifts involved, in your reaction. Okay, so let's solve this example 4. Okay, so we start with protonation of the OH group. Okay, your oxygen will attack this hydrogen and this bond will break heterolytically. So we are making this protonated alcohol group. Okay, so CH3 with OH and H here, so with a plus charge, and we leaving us with a nucleophile. Okay, so this nucleophile will be useful at the last step. Okay, so from here, so there will be a loss of water to form your carbocation. Okay, so this bond will break and we're going to form this carbocation with the removal of water molecule. Okay, so the plus charge here and CH3 plus water. Okay, so from here, so we're going to do 1,2 hydride shift because in these examples we are making a secondary carbocation. So I want a more stable carbocation. So what will I do? I'm going to do 1,2 hydride shift. Okay, so this hydrogen here will be transferred to this carbon in the carbocation. Okay, so we are making a tertiary carbocation, which is more stable than your secondary carbocation. Okay. Alright, so this is your tertiary carbocation. So from this, okay, so we're going to lose H plus. So where we're going to use the nucleophile that we produced initially, which is your O negative SO3H. Okay, so the negative charge from your sulfate ion, okay, will attack this hydrogen and the bond will break heterolytically to form a double bond. So here is our alkene. Okay, so CH3 with regeneration of your sulfuric acid. So this is your major product. Okay, so let's check your understanding by doing exercise 1. Okay, so you need to propose a mechanism for the dehydrations of 3-methyl to pentanol to form major and minor products. Okay, so this is the skeletal structure of your 3-methyl 2-pentanol. Okay, so it starts with 2 basic steps. Okay, which is protonation of OH group, okay, by using your sulfuric acid. Okay, so first, okay, so we're going to make a protonated alcohol. So this lone pair from your oxygen will attack this hydrogen and the bond will break, so leaving us with a nucleophile and a protonated alcohol. So OH2 with a plus charge, okay, plus your nucleophile. Okay, next, okay, so this protonated alcohol, so the water molecule will leave, okay, breaking of the bond. So we are making a carbocation. Okay, so this is the plus charge plus water. Okay, so here we have your secondary carbocation. Okay, so in order to form your major product, you need to do 1,2 hydride shift so that we can form tertiary carbocation. And if you want to do minor products, that means there will be no carbocation rearrangement. We can proceed with the last step, which is the removal of H+. Okay, so please continue your reaction mechanism from here to show us how do you form major and minor product. Alright, so I'm going to leave you with the second exercise, okay, where you need to show the reaction mechanism for the formation of these 3 alkenes. Okay, 1 is major product and 2 is minor product. Actually, there will be another 1 minor products, but I'm going to stick with these 3 different types of alkene. All the best to you. See you guys in the next video. Bye bye.